Good afternoon, everybody. Thanks for joining us. I see we have a lot of people already online here. It's just good to give everybody another minute or two to make it for an on-time departure here. All right, everybody. It's 3:01. Thanks for everybody who joined us on time. Let's be mindful of everybody's time and let's get started. So in this case, or to start it off, I'll say welcome everybody to our threaded inserts and compression limiters for plastic assemblies webinar. My name is Markus Späth, and I have the pleasure of moderating today's webinar. I joined SPIROL 4 years ago, and after managing our US OEM sales team for the past 3.5 years, I've taken on the role of Global Automotive Key Account Manager. In that role, I'm responsible for the global coordination of SPIROL resources to ensure that our automotive OEMs are best supported by our globally local teams. Now, with me, I have Tara Mink. Tara is our product manager for the Metal Cut product division. Tara started her career at SPIROL as an application engineer and has specialized in our threaded inserts and compression limiters for the past 10 years. As the product manager, she drives our product development, go-to-market strategy, and is an extension to our technical sales team. Now, today she will be here for live support to questions that might arise throughout the presentation. So please feel free to share all your questions as they come up using either the Q&A function or the chat function here in Teams. Our intention is to answer all your questions at the end of the webinar for a shared mutual learning experience. And if you would like us to follow up privately and not read out your questions, please reach out to us separately and we will get back to you right after the webinar concludes. You will find our contact information at the end of the webinar. Now, for the presenters of today, you will be guided by my colleagues Arthur Kisby and Sean Horton. You will see them on the screen right now. Sean, our US OEM sales application specialist, has over 30 years of experience in the automotive and automation sector. With his hands-on knowledge, Sean helps both OEMs as well as tiers to design joints that go together and stay together for the intended life of the product. All that at the lowest cost of the assembly. Applying his experiential knowledge early in the design process is really key to making this happen. Now, for Arthur, our technical sales representative, he has been part of SPIROL for more than 7 years. During his time, he has worked across various regions within the US, focusing on a multitude of applications. Arthur prides himself in being a solution provider, working in collaboration with his customers in developing both commercial and technical solutions with the goal of lowering costs as well as improving performance. You will see two of our best in the next hours or so. Now, before I pass the mic to Sean and Arthur, let me remind you one more time, we want to engage with you here. So please feel free to post your questions via the Q&A and chat function as they come up. With that said, Sean and Arthur, the show is yours.
Thank you, Marco. Thanks. I'll briefly go over what we'll be covering in today's webinar. To start, we will cover how to ensure the continued integrity of a bolted plastic joint through the proper selection of threaded inserts and compression limiters, common types of inserts and compression limiters, associated design guidelines for plastic components that use inserts and compression limiters, an overview of the relevant terms and concepts. But before we get into this, I want to give a brief overview about SPIROL itself. SPIROL is a global manufacturer and supplier of engineered components used for fastening, joining, and assembly. We have 12 major product lines, each one designed to improve product quality, simplify assembly, and/or reduce total cost of assembly. We're the only company who designs and manufactures both our engineered fasteners and installation equipment. Our focus is not just about supplying a high quality product, it's on partnering with our customers as early in the design stage as possible to aid them in design. This is not only for the fastener, but also to make critical recommendations between our product and their components so that their assembly goes together and stays together for the intended life of that assembly. At present, we have 15 locations around the world and have applications engineers at each of those locations. We're ready to work with you on your new and existing applications. Today's webinar is focused on inserts and compression limiters for plastic assemblies. So, where are inserts and compression limiters really used? The answer is pretty much everywhere and in every market, such as automobile, agricultural equipment, rail, recreational vehicles such as snowmobiles, jet skis, and boats. They're used in home appliances, medical equipment, hand and power tools, industrial equipment, and airplanes. They're literally everywhere. In both ICE and EV automobiles, you will find SPIROL products across a multitude of assemblies.
Some of the specific applications within these markets can be seen here. In the top left, we have compression limiters used in a front engine cover, so that when the cover is bolted down, these limiters provide spot reinforcement to prevent the plastic from cracking. Next, you'll see compression limiters in an intake manifold, and then compression limiters used in a residential charging connector. These are used for solar-powered homes. In the lower left-hand corner, there's an example of threaded inserts used in high voltage switch assembly, and then an oven handle where the bolt is threaded into the metal insert rather than directly into the plastic to ensure joint integrity over the life of the major appliance. And finally, you will see an automatic pool cleaner housing where there's literally dozens of inserts used on both sides of the plastic component. When discussing the performance of compression limiters and threaded inserts, it's important to tie them back to the bolts that are being used in conjunction. While bolt performance is defined by an industry specification that outlines how much force the fastener can withstand before breaking, the proof load is the maximum load that can be applied without risk of permanent deformation. This is when the bolt won't return to its preloaded condition after the joint's loosened. The clamp load, on the other hand, is how much load is applied to the bolt when the joint is tightened. SPIROL recommends that a joint is tightened to clamp load somewhere between 25 and 75% of the proof load, due to the relatively large tolerances associated with torque measurements. The amount of load a bolt can withstand is typically defined by the bolt's thread size and length, grade for inch bolts, and class for metric bolts. What's displayed on the screen here are the most common bolt specifications defining bolt strength. This table illustrates each thread size's tightening torque and clamp load specifications.
So, why do people use threaded inserts in plastic? Well, first and foremost, inserts provide reusable threads and form secure, tight threaded joints. Since you thread directly into metal rather than plastic, you have unlimited assembly and disassembly without fear of stripping the threads. You're able to meet the proper seating torque for the bolt. Of course, that's if the integrity of the plastic is there. Unlike when you thread directly into plastic, you don't have to worry about creep or stress relaxation that could result in a loose joint. And finally, given that the OD of the insert is approximately 2 times the OD of the bolt, This results in 4 times the shear surface for enhanced load carrying of the bolt assembly. Now, before we talk about what types of inserts are good for a particular application, we need to review that there are 2 major types of plastics: thermoplastics and thermosets. Thermoplastics essentially can be melted and remelted several times into several different shapes without compromising the mechanical properties, whereas thermosets have a one-time reaction from liquid to solid and cannot be remelted. Both thermoplastics and thermosets can be strengthened using glass or mineral fillers. Usually the higher percentage of the filler, the stronger the plastic.
SPIROL's threaded inserts are categorized by the primary method of installation. While some of the inserts are designed to be overmolded into plastic, allowing the molten plastic to flow around and into more aggressive retention features, most of our inserts are designed so that they can be installed in a secondary process after the plastic has cooled. We refer to these types of inserts as post-mold inserts. Post-mold inserts can be installed in a variety of ways, by either locally remelting the plastic with a heat or ultrasonic installation, by pressing them into the plastic cold, or even screwing them directly into the plastic. Inserts should be designed with sufficient torque resistance to accommodate the tightening torque needed for the bolt to prevent loosening, as well as enough pull-out resistance for the loads they'll face while in use. In general, the resistance to torque, that rotational torque rather, is a function of the insert's diameter, while the resistance to pull-out, also known as tensile, is a function of the insert's length. The designer's challenge is to determine the best balance between these 2 design criteria and optimize performance within the space allotted. As we are very much aware that space is often limited within your assemblies, so we're here to help you through the process. As an insert's length is so critical, we offer almost all the styles that we have in both a short version and a long version.
Now, the internal threads of inserts are designed around industry standard metric and inch bolts. Performance of the insert is generally achieved based on the amount of displaced plastic filling the various types of features of the insert. There are typically 3 different types of knurls: diamond, straight, and helical, and they are primarily used to increase resistance to torque. Straight knurls have the best resistance to torque since they are perpendicular to the force, whereas helical knurls provide resistance to both torque and pullout, as they are at an angle. Finally, diamond knurls, well, frankly, they aren't good for anything, really. The reason being is that if you press a diamond knurl part into plastic, the diamonds literally shred the plastic during insertion. The most popular type of insert where diamond knurls is found is on what they call an expansion style insert, here in the upper left. As you can see, there's a slot on both sides of the insert. You push it in the hole, the slot closes. As the bolt is installed into the insert, the bolt makes the slot open up. The diamond knurl is supposed to bite into the wall, but in reality, the performance is pretty low and the cost is much higher. SPIROL has since replaced the expansion style insert with a press-in style that have much higher performance and a much lower cost. Other performance features are barbs and undercut, as shown in the insert in the bottom right. This style, in this style of displaced plastic flows into the undercuts, and then the barbs help prevent the insert from pulling out of the plastic.
There are many different. Sorry, go ahead,
types
Sean.
of plastics. Sorry. There are many different types of plastics. In order to specify the best insert for a particular application, it is critical to understand the plastic specifics, meaning not just whether it is thermoplastic or thermoset, but what specific type of plastic it is, the percentage of fill, and the type of fill. If possible, the brand name of plastic, such as a DuPont Nylon 66 with 30% glass fill. We also need to understand the geometry of the host component, including available space for hole diameter and wall thickness. what bolt size you're planning on using, what's the grade or class of bolt you're going to be using. This is very important because, as I was mentioned earlier, the class or grade actually dictates what the recommended tightening torque is for that bolt size. Now, we also want to make sure we understand what the performance requirements are for the application, torque and pull-out or tensile strength, and what the mating component configuration is. And finally, how do we plan on installing the insert? Is it mold in or is it post-mold installed? If post-mold installed, will it be simply pressed in the assembly, tapped into the hole, or heat ultrasonically installed?
There are many factors besides an insert's design that affect how it will perform in the assembly. As the quality of the interface between the insert and the plastic component is so critical to how much the insert can withstand torsional and axial loading, the quality of the insert's installation is paramount. These images demonstrate how SPIROL recommends validating the installation quality through a destructive test. We recommend cross-sectioning the plastic after the insert gets installed so that this interface is clearly visible. After the insert is removed from the plastic, a mirror image of the insert's features should be present in the plastic. As you can see in the incorrect example on the left, the knurl's imprint of the plastic is very shallow, and there doesn't look to be any evidence that the barb actually engaged with the plastic at all. Also worth noting, there shouldn't be any voids present between the insert and the plastic. Although some common errors that lead to poor installation are listed to the left, the example shown here appears to be the result of a hole size that was a bit too large. Not enough plastic was flowing into all the retention features in the knurls. It's not just the interface between the insert and the plastic host component that are critical to performance. The mating part can also significantly reduce resistance to rotational torque when it doesn't support the top bearing surface of the insert. We call this condition jackout. When the hole of the mating component is larger than the face of the insert, there is nothing to prevent the insert from dislodging and moving up into the void of the mating part. To avoid jackout, we recommend that the mating component's hole is smaller than the face of the insert, but large enough to allow the bolt to pass through. One strategy you could implement is to use a flange or a head on the top of the insert to increase the bearing area. It's worth noting that using a headed insert does increase insert costs due to the additional material needed to form the head.
When installing the insert into the hole, the top of the insert should be as close to flush with the surface as possible. The maximum protrusion above this flush should be 0.13 millimeters to or 0.005 inches. You really want to be careful about having the insert subflush, or else you risk, again, jacking out the insert out of the hole, or at least breaking the plastic plane while torquing down the bolt, which could affect the joint integrity. In terms of hole configuration, the diameter of the plastic around the hole, known as the boss diameter, should be sufficient enough, typically twice the OD of the limiter itself, to avoid bulging during installation and ensure integrity to withstand the recommended tightening torque. Also, in the event that it is a blind hole, the length of the hole must be long enough to prevent the screw from bottoming out. For heat ultrasonic installation, the link must be plus 2 threads to allow the flash or material built up ahead of the insert a place to flow during installation.
The hole size of an insert gets installed into is also critical for the insert's ability to perform in the assembly. For inserts that are used in straight holes, it's recommended that the taper doesn't exceed 1 degree inclusive, or a half a degree per side. For inserts intended to be used in a tapered hole, we recommend the taper to be 8 degrees, or 4 degrees per side. Using an insert designed for a tapered hole assists with removal of the plastic component from the mold, but also allows the insert to sit deeper into the hole prior to the installation, facilitating square and faster installation. Regardless of the hole style, it's imperative to hone in on the correct hole size for the application. As a general rule, larger hole sizes decrease performance, while smaller hole sizes may induce undesirable stresses and potentially lead to cracking. The recommended hole size found in our design guidelines will typically need a slight positive adjustment, if any. Usually, the hole size needs to be adjusted upwards further when the plastic type is more viscous or it doesn't flow very well, such as when fillers like glass are used. In the example shown to the left, no filler is being used and the plastic is polypropylene. Noting the recommended hole size for an M6 heat installed insert is 8 millimeters plus 0 minus 0.08 millimeters. However, if that same component was made of nylon 6/6 with 35% glass fill, we'd recommend adjusting the initial hole size up by 0.15 millimeters. It's also important to emphasize that the core pin used to mold in the hole should be appropriately sized to allow for plastic shrinkage after cooling. The hole size should be verified with a plug gauge post-cooling. In summary, it's imperative that a designer perform testing to validate the appropriate hole size for the application, not just rely on the recommended hole sizes we publish in our catalog. Complementary application engineering service SPIROL offers can assist with this sort of testing.
In high-load applications, a headed insert with the head located opposite the load in a pull-through configuration is a design consideration that may be warranted. Tapered inserts should never be used in a pull-through applications or in thin-walled bosses, as they will cause cracking of the plastic. Each type of insert differs in design, which yields different performance results, as well as the cost of the insert and the overall cost of the assembly. Starting with heat ultrasonic inserts, some are designed for straight holes and others for tapered holes. If you attempt to use a straight insert in a tapered hole, the performance will not be optimal. In many cases, you may end up totally cracking the plastic. Symmetrical inserts require straight holes. As Arthur just said, tapered holes facilitate proper seating of the insert, and since the surface contact between the insert and the hole is maximized, installation time is usually less than that of a straight insert of the same size. Many heat ultrasonic inserts are available in both a long and a short version of each thread size. Long lengths maximize torque and pull-out resistance, while short lengths are good for less stringent requirements at a lower cost and shorter installation times. You can also get most styles with or without a head. The head provides the bearing surface for the mating component that also prevents jackout, or when used in reverse can prevent pull-through. However, adding a head comes at a cost because you have to start with a larger piece of raw material to create the head. A symmetrical insert design eliminates orientation issues during the installation process. You can achieve excellent performance results with heat ultrasonic inserts provided they are used in the proper hole size and sufficient wall thickness around the insert, and they're installed with proper melting of the plastic to fill the voids of the insert. Heat ultrasonic inserts generally provide the best balance between performance and cost. Notice the external thread on the self-tapping inserts. This type of post-mold installed insert is actually threaded into the hole after the plastic cures. The external threads are designed with a thin profile to maximize stress in the plastic, to minimize stress in the plastic, and relative coarse pitch to provide maximum plastic shear surface to resist pullout. As a matter of fact, these provide the best resistance to pull out of any SPIROL's post-mold installed inserts. However, due to the external thread, the manufacturing cost of the insert is usually higher than other types of inserts, and the cost of installation is the highest of all post-mold installed inserts because of the care and time that it takes to thread in to the part. The schematic in the lower right shows the recommended length of hole for this type of insert is 20% longer than the length of the insert. Counterbores are typically not recommended for any insert except self-tapping or headed inserts. Counterbores are recommended for self-tapping inserts to reduce the risk of flaking. The outside diameter of the counterbore should be equal to or larger than the outside diameter of the self-tapping insert.
Our press-in inserts, on the other hand, were designed to reduce installation cost. Instead of the large exterior threads you find on the self-tapping inserts on the previous slide, these types of inserts have helical knurls to provide both torque and pull-out resistance without the need for screwing them into the hole. As you can see in the illustration, a pilot facilitates straight insertion into the hole, and since the pilot diameter is smaller than the hole, and the length is long enough to allow the insert to sit in the top of the hole before installation, they're a great low-cost option for applications that don't require super high performance. Press-in inserts are available with or without a head, and we offer them both in brass and in aluminum. For applications that require the highest performance, our molded-in inserts are designed for maximum pull-out and torque resistance. These are often the inserts of choice for thermosets, which is the types of plastics that can't be remelted, as plastics with much higher percentage of filler. The minor thread diameter tolerance on these overmold inserts are tightly controlled to provide a repeatable fit on the core pin that's used during the molding process. SPIROL offers a symmetrical through-hole version that eliminates the need for orientation, as well as a blind end version, which sometimes is preferred by some of our molders. These are made out of 2024 aluminum, a lightweight, lead-free grade.
So, in terms of using post-mold installed or molded-in inserts, there are many factors to consider. When installing inserts after molding, it reduces in-place cost as the molding time is shortened since there is no placing of the inserts over the core pins. Secondary cleaning of flash or plastic around the entrance of the hole that often occurs with mold-in inserts is also eliminated. Installing inserts after molding also reduces rejects and the chance of mold damage resulting from a dislodged insert. You must keep in mind that some molds cost tens of thousands of dollars. And finally, post-mold installed inserts can yield excellent performance results. Conversely, when molding inserts into the assembly, the molding time is increased as you have an operator or a pick-and-place robot loading the inserts over the core pins prior to being able to close the mold cavity. The precise placement of the inserts is required, otherwise mold damage can occur, which again can be expensive in both repair and downtime. That said, you do get the best performance out of molding inserts over any other. The question is, what performance do you require for your assembly?
So what affects the performance of an insert? In fact, there are many variables that impact insert performance within the application. Not only does the insert design, quality of the features such as knurls, barbs, and undercuts, but also the type of plastic. For example, an insert installed into nylon 6/6 with 30% glass fill will totally outperform the talc-filled polypropylene as it's much more rigid. The design and quality of the plastic molded part also plays a huge role in performance. Like, are there any knit lines in the boss surrounding the insert? Is the wall thickness of the plastic sufficient to handle the applied stress? Obviously, the hole size will also affect performance a lot. Even hole size variation within the recommended tolerance range found in our catalog will result in different performance. And finally, the quality of installation process impacts performance as well. So, was the proper temperature used? Were the inserts installed too quickly, etc.? Another common question we often get is, what temperature do I use for the installed inserts, and what pressure should I apply? We recommend starting with a temperature 50 degrees Fahrenheit above the initial softening temperature for the plastic in question. But for plastics with fillers, its initial differential should be increased to about 150 degrees Fahrenheit. Pressure is insert size dependent and should be as low as possible in like the 5 to 15 psi range. And the pressure should be just enough to push the insert into the hole as the plastic melts.
So how do you know if you have a properly installed insert? This is most definitely a destructive test that you need to perform, maybe even a little barbaric. We would literally take a hacksaw and section the plastic component with the installed insert in half, then pop the section insert out of the hole and ensure that the features of the insert are mirrored in the plastic, as shown in the image on the right. It's extremely important to ensure proper plastic flow into the features of the insert, as this dictates the torque and pull-out performance you achieve. As you can see on the left, the plastic did not sufficiently flow into the retention features, which will result in low insert performance. By far, the most common question is how much torque and tensile strength can be achieved with the insert in my specific plastic assembly. It is impossible to answer this without testing it in your actual assembly. All of the factors we've just went through a couple of slides ago affect performance. In addition, there are so many different types of plastics and fillers coupled with the complexity of component design. SPIROL provides a section in our insert design guide that displays the performance of various styles of inserts installed into a nylon 6/6 without fillers in drilled versus molded holes. This performance data is provided as a comparative guide between insert types, not to provide actual performance. For this, you need to test.
Okay, so now we'll start to talk about compression limiters. Just so you know, this section of the presentation will go a bit quicker since a lot of the same concepts apply. Consider these as like a sister product to the inserts that we've been discussing. So what are compression limiters? Essentially, compression limiters are spot reinforcements of metal used in plastic assemblies, and they're designed to protect the plastic from cracking or yielding under the compressive load of a bolt. We implement compression limiters so we don't stress plastic components beyond their elastic limit. The ability of a compression limiter to carry a compressive load is determined by two factors. One, it's the strength of the material. And two, it's the cross-section area of that compression limiter. Limiter strength can be increased by increasing either the wall thickness, increasing the strength of the material, or a combination of both of these factors.
There are two critical design rules to consider when using any compression limiter. Rule number one is that the bolt or washer must contact the compression limiter. This condition must be met without exception. If the bolt does not contact the limiter, it will result in plastic creep and ultimately loss of compression over time. The image on the right would not be acceptable if the bolt was was fully torqued down. In this case, the compression limiter is doing nothing at all. It's just adding cost to the assembly with no value. The image on the left shows a properly bolted joint.
Rule number two is the plastic should have a small amount of compression. If the plastic is not compressed, the hose component may move about the limiter. By the way, it's important to note that the delta showing in the gap in this image that you're seeing on the screen is only there prior to the torquing down of the bolt. Once the bolt is actually tightened down, the plastic needs to be compressed to get that metal on metal on metal contact Sean was just mentioning. That is really just a non-negotiable.
In order to properly evaluate an application and determine the most appropriate compression limiter, The following needs to be understood. It is both that, excuse me, it is important that both the bolt size and the class or grade is known, as this will dictate the recommended tightening torque, which ultimately determines how much force the compression limiter must withstand. We also need to understand the max allowable compression of the specific plastic. Most plastics can compress between 5 to 15%. The plastic thickness and compression limiter length tolerances are also very important. Ideally, the maximum compression length be equal to or below the minimum thickness of the plastic without exceeding max compression. See how this is all intertwined with each other? The yield strength of the mating component is also important, as you don't want to indent the material of the mating part, creating witness marks. When the bolt is torqued to the recommended tightening torque. And finally, we want to understand the environment in which the compression limiter will be exposed, as we want to understand both the environmental and the galvanic corrosion requirements.
So here's an example of how we use some of the information we've just been talking about. If we don't have any information about the plastic's modulus of elasticity, we will assume a conservative compression of 3%. In this example, the customer is in the early stages of design and has selected our M6x20 long compression limiter. And they're looking for our feedback on the plastic thickness tolerance to apply. Remember, there are two rules for compression limiter length as it relates to the plastic thickness. One, the compression limiter must bottom out against the mating component of the bolt head or washer once the bolt is tightened. And two, ideally the plastic will have a slight amount of compression when the bolt is tightened. To achieve both of these design criteria, the maximum compression limiter length should be equal to the minimum plastic thickness. In this example, we know that the length of the compression limiter is +0 minus 0.15 millimeters. And since we want the minimum plastic thickness to be 20 millimeters, which is the sealing length of the compression limiter, we want a positive tolerance on the plastic. In this example, we're assuming that the molder can maintain a 0.1 millimeter tolerance. So knowing this, we can calculate the stack-up tolerance of 0.15 millimeters plus the 0.1 millimeters equaling 0.25 millimeters. If we compare the tolerance stack-up to the allowable compression, or 3% of the 20 millimeter length, it's about 0.6 millimeters. So we can see that the stack-up tolerance isn't going to be a problem, as it's less than the amount of plastic than the amount the plastic will be able to compress safely. So now, to tie in the rest of the information we require when making recommendations for compression limiters that we just reviewed. So we discussed bolt size, class, and grade, compressive load created by the bolt, and talked about the clamping load being 75% of the proof load. We have the maximum allowable compression of the plastic, known as the modulus of elasticity. Most plastics can compress between 5 and 15%. Plastic thickness tolerance, compression limiter length tolerance, mating component yield strength, and corrosion resistance requirements. So, in the bolt, is the bolt strong enough to compress the plastic? Okay. Well, this scary looking equation is how you calculate this, but for some time considerations, I'm not going to go through all the details, but it will be included in the presentation that will be emailed to you in a couple of days.
So in terms of selecting which type of compression limiter is best for your application, there are a variety of compression limiters available. They're usually designed around standard bolt requirements and the method of installation. The overarching difference between the limiters is that some are rolled from steel and some are machined from aluminum and brass. Within the roll form steel category, we offer circular shape with split seam or for post-mold installation, or a butted seam for molding in. These are also offered with an oval shape to accommodate a wider tolerance in one axis for easier alignment, which is particularly useful when you're using multiple limiters in an assembly. Within the machine category, they can be installed either by pressing in or molding in. You don't need to specify a particular machine version to match the installation method. A head can be added to increase the bearing surface against the mating component of the bolt, or the bolt rather. Unless there's a concern with galvanic corrosion, aluminum is generally preferred over brass because it is lightweight, lead-free, and stronger than brass. In terms of how to choose between machined or roll form limiters, the reality is that when it makes sense, rolled steel is definitely the most economical option. However, for short compression limiters, particularly when the length of the diameter ratio is less than 1, it makes most sense to use a machine limiter because it is difficult to roll a limiter that's short and keep the ends square. Also, machine limiters are preferred in mold-in situations where the plastics have very low viscosity, since there are no seams for the plastic to seep into. Machine limiters can be supplied with a head for a larger bearing surface for soft mating materials. A head also eliminates a washer. In most cases, though, we suggest just using a flange bolt instead. Finally, if you're going to use a machine limiter, we recommend aluminum over brass, again, since it's lighter, stronger than brass, and lead-free. As I said a few minutes ago, rolled steel limiters are less expensive, and they can also be heat treated to withstand higher tightening torque. The split seam is designed such that the part is pressed into the assembly, whereas the butted seam is suitable for molding in with viscous materials. Also, as we mentioned in the last slide, the rolled steel versions are available in an oval configuration as well as the circular for extra clearance on the one axis, as we see in the application here in the right of the slide.
So, to summarize design considerations for compression limiters that we've been covering, the most important criteria that you should take away from this is the need for metal on metal on metal contact, or bolt flange on compression limiter on mating component contact when the bolt is tightened. Remember, without this, you're adding cost to the assembly with not really any compression, without the value of any compression limiter, as it's just floating within the joint. Ideally, we want some plastic compression of the plastic, as it does tend to relax over time, and we wouldn't want the plastic host to shift up and down along the length of the limiter. In some instances, achieving this may be difficult, especially in cases where the plastic host is on the thinner side and your mold can't hold super tight tolerances. So we implore you to consult with us so we can provide more complex recommendations when required. There are always ways of achieving the critical metal on metal on metal contact to optimize your joint, while also maintaining some plastic compression. In some instances, though, we'd want to partner with you in order to provide application-specific recommendations. Well, just like with the plastic, we also need to make sure that the bolt does not exceed the elastic limit by assigning a clamp load of about 75% of the proof load. If an insert's used, like in the example shown, the limiter should be well aligned to prevent a jackout condition. And lastly, the hole size is critical to ensure that the compression limiter can retain its position within the assembly prior to the bolt being assembled.
In conclusion, think about inserts and compression limiters as early as possible in the design stages of your project. This will help you design in standard components, which reduces time and cost since they can likely be supplied from stock. Also, don't overspecify your requirements. If you say to a manufacturer, just give me the insert with the highest torque and pullout, when you don't really require that kind of high performance, you're going to pay a lot more than you need to. When designing your assembly, use proper design parameters. Please do yourself a favor. If switching from one supplier to another, provide the actual performance requirements versus just saying, give me the same high performance as the one I'm getting now with my current parts. Because recognize that if you ask one manufacturer to make the same exact part as someone is already making, you're going to usually pay more for the new manufacturer because we're not set up to make that part. Finally, but above all, make sure to test the bolted assembly to ensure the performance requirements are being met. Now, if you're interested in learning more about inserts and compression limiters, I encourage you to visit SPIROL.com. That's SPIROL.com, and download the application stories and white papers. We literally have over 100 on white papers.
Also, we have 3D models of all of our products available on our website that you can download, or you can insert directly into the model of your assembly.
If you're working on a new involve SPIROL as early as possible. I often hear, but I have not even designed the hole yet. Perfect. That's exactly when you want to bring us in. So we can aid you in sizing that hole and help determine the lowest total cost method of joining. We will conduct a comprehensive evaluation of your application and then provide you with a detailed engineering report. If the solution is in our inventory, we'll be more than glad to even provide some samples for testing and approval. Okay, Marco, I am sure we have received some questions throughout the presentation that I guess we'll review now.
Absolutely. Thank you, Sean. Thank you, Arthur, for guiding us through the presentation here. We did get 5 questions so far, and I want to make sure we take care of all of them. But there's one that I'm going to reply to you through the chat function because the question came in. I'm going to read it for everybody anyway. It was, could you provide mating compression limiter design considerations that interact with insert? Great question. It came in when we were talking about inserts. So I hope we answered that question with the second half of the presentation just after you posted the question. I'm going to reply to you privately through the chat here. If we did not answer your questions, please just reply back to us and we'll pick that question back up. I don't want to dismiss it though. The next question was, what sizes do you have available for inserts and compression limiters? I'm not sure, Arthur, you want to take that one?
No, I'll take that. So we try our best to provide a wide range of options for our customers. We have a good pulse on the industry, so we believe that the offering that we have in our catalogs that you can get on our website are pretty extensive. So, but to answer the question more directly, like for an imperial sizes, they range from like the inserts particularly 256 up to 5/16, you know, in thread sizes, and the metric range from like M2 up to M8. But we do have the ability to make custom sizes. So please bring your opportunities to us so that way we can work on them. As far as compression limiters go, the compression limiters we offer range. And again, our compression limiters are designed to be used in conjunction with a bolt. So when I refer to the sizes for compression limiters, I'll say that for limiters of M4 to M12 is what we offer as a standard.
Awesome. Thank you, Arthur. I hope that answered your question as well. If you have more questions, follow up in the chat or via the Q&A function. The next question we had was, what are your recommendations concerning installation to maximize performance? And the same question also, what is the performance difference between molding in, heat insulation, or ultrasonic insulation of the same inserts? All right, not sure, Tara, do you want to give this one a trial?
It's a tough one. Take that one. Absolutely. So SPIROL typically would recommend pairing the installation method and the insert along with the associated application requirements for performance. So typically rotational torque and pullout. Generally speaking, and this will vary depending on the maybe the molder that's actually processing the inserts and what their I'll say setup is in terms of manpower and capability and their preferences. But generally speaking, SPIROL recommends reserving overmolding as something for applications that really have stringent performance requirements. So to kind of touch on the second half of that question, where you're looking at varied methods for installing the same insert, generally speaking, if you're able to get away with a post-mold installation that can occur outside of that molding process, that may make that process more efficient in terms of separating the molding from and being able to have that mold running at an optimized speed, and then having that secondary operation occurring for getting the insert into the plastic component. Generally, that would be the most cost-effective method to get the performance out of your application.
Awesome. Thank you, Tara. The next question I have on here, I'm going to read it and I'm going to have to add my own interpretation. I apologize if I misinterpret it. The question is, how much torque as a minimum threshold the compression limiter be used if I have a Polypro glass fill 30 or a PA6, like a nylon 6, with a 30% glass fill? Can there be an added rib or web structure around the hole to sustain the torque without a compression limiter? And if yes, then to what level, as in min or max, right? And provided the wall thickness is 3 millimeters in both cases. Happy to bring the team in here as well, but my understanding is that we would recommend to have a compression limiter in the plastic no matter what, right? Because there's really two failure modes. The obvious one is that if you bolt it down, that you crack the plastic right off the get-go, right when you assemble it. The second failure mode is that over time, the plastic creeps away from that stress and you lose the bolt stretch, right? Because when you're bolting something together, you want to stretch the bolt to maintain that snug fit. And if the plastic creeps away, the distance shortens, the bolt loses its stretch, and you lose that performance in the assembly. So therefore, we would suggest using a compression limiter whenever you have a, I guess, plastic assembly that needs to be bolted together. Now, I'm sure there's applications out there where maybe you can get away without it. I mean, if you're bolting a kid's toy together, maybe you can get away without it. I think we've all seen those, but for automotive applications, which I think is the majority here, we would typically recommend the use of a compression limiter. I hope I interpreted that question correctly. If I did not, again, I'm going to reply through the chat here. Please let me know if you have further questions. We'll pick it back up. Next question was, how are tariffs impacting your inserts and compression limiters? Not sure, Sean, do you want to give this one a trial?
Boy, sure. Well, as far as tariffs are concerned, we've been working very hard to mitigate cost risk associated to that, partnering with different companies and looking at our overall production stance so that we can actually help reduce tariff impact. The best case, though, contact us. Let's work together, see what we've got going on, how we can help you individually. It affects us all differently, so that's the best course.
Awesome. Thank you, Sean.
Hey, Marco, I see somebody add a question in the chat instead of the question and answer area.
Oh, okay.
And since I believe I went over this topic, if you don't mind, let me just switch slides over. Sure. The question is, can you go over jack out again? I'm just going to pull up the image that shows the cross section of our ideal bolted joint real quick, and okay, it'll be able to show this very briefly here. Okay. So in a jack out condition, you can see the compression limiter that is surrounding the threads of that bolt is mated up against the washer above that limiter, as well as bearing down on the insert itself. Now, in a jackout condition, that limiter would have too large of an ID. So that inner diameter would be farther out wide, allowing as the torque to be applied to that bolt to pull the insert into the void of the insert of the limiter in this example. So I feel as though that might help give you a visual on what a jackout condition would be. Pulling the insert, dislodging it from within the host material, instead of having a metal on metal on metal contact.
Awesome. Thank you, Arthur. I almost overlooked the one in the chat. Now I get one more in the Q&A. It was, we use steel inserts because they are most economical. Do you offer those as well? I guess that's a product manager question.
I can take that one. Sure. So at this point in time, we actually don't offer any steel inserts. And that's for a few reasons. One of those is, generally speaking, the steel is going to require some sort of supplemental finish or coating to ensure that the fastener is going to have corrosion protection. And with an internally threaded fastener, the risk there becomes ensuring that you have a consistent coating along the thread of the fastener. And sometimes with those internally threaded components or with a hole, that coating can become inconsistent in size. And because the thread is so important for the function in the assembly, as well as it's a feature that oftentimes can't be 100% checked for compliance, understanding the automotive industry's, let's say, expectations surrounding quality. That's something that for that one reason, we kind of shy away from using ferrous materials that have that inherent environmental corrosion. Another consideration is, depending on the installation method, a lot of times these fasteners have to be heated up in order to be introduced into the assembly and be able to provide performance. And during that process, the steel can become corroded, whether it is sealed or not. So for those reasons, mainly surrounding corrosion expectations and expectations of our customers and the applications that they're used in, we typically stick with non-ferrous materials a la brass and aluminum.
Awesome. Thanks, Tara.
You got it.
I think, unless I'm missing another question, Arthur, if you see more, pick them up. I think that's all the questions I'm seeing right now. If you have more questions, we'll give you another couple moments here.
I had one point to add. I was asked this question right before joining this meeting from a customer, and I thought it would be appropriate to bring up. So the question I had was, how much pull-out force do our compression limiters provide? Well, that question I actually get asked quite often, right? In the same context that you might ask for the inserts that we offer. Well, it's kind of a trick question. The compression limiters are designed specifically to engage with the host material they're installed into, but they're really not designed to withstand very high loading axially. So their job is to stay within the plastic component host until the bolt comes in and it moves along the manufacturing line for the bolt to encapsulate that limiter within the assembly. So I thought that we didn't really go over that concept throughout the presentation, so I wanted to add that in if anybody was thinking.
Great addition. And I think in the same vein, it goes into compression limiter, right? Not a compression prohibitor. So make sure the compression limiter actually absorbs some of the compressive loads that we're applying to it and not prohibits it from being transferred to the plastic at all. That's a common one as well. All right. I don't think I see anything new at this point. So I appreciate everybody who joined us today. Thanks for the great questions we got here. If you have more questions, don't be shy to reach out to us. Appreciate everybody's attendance.
Hey, before we head out, maybe we should take a screenshot of the screen here that we have open, considering that our email addresses are out there. So Sean Horton and Arthur Kisby, please reach out to us if you have any questions, if you think about them in the next few days.
Absolutely. Absolutely. And on behalf of the group here, thank you again for attending today's webinar. Please feel free to contact us at any time. If you have any questions regarding inserts or compression limiters, we'd be more than happy to help you. And thank you very much.
Thanks again, everybody.
Take care. Thank you.
Take care. Have a good day.